Good morning, good afternoon, and good evening, everyone. Dear authors and invited guests, welcome to Technical Session 7A. I'm Sanskriti Kamkar, and I will be moderating this session today. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my pleasure to welcome you to the 11th International Congress on Information and Communication Technology, that is ICICT 2026, in London, UK. This edition of the conference is being conducted in a hybrid mode. The physical event was held on the 24th in London, and the virtual sessions have been conducted via Zoom from 25th to 27th February 2026. I hope you find today's session engaging, informative, and insightful. In this session, we have 6 presentations. Each presenter will have 12 minutes for their presentation, followed by 3 minutes for Q&A. I will raise a gentle reminder when 2 minutes remain. I request all participants to stay connected until the closing remarks. If you have any questions or updates, please feel free to share them in the chat box. I'd also like to apologize in advance for any mispronunciation of names during this session. Now, before we begin, I'd like to introduce our session chair, Dr. Ridhima Dhillon. She's a professor at Lovely Professional University in Punjab, India. She specializes in marketing, consumer behavior, and the application of artificial intelligence within management. Her key research areas include AI in marketing, service marketing, consumer behavior, and information technology, with a particular focus on data-driven and technology-enabled marketing strategies. Now let us proceed with the presentations. Our first presenter is Xiaofeng Liu, presenting a deep reinforcement learning approach of congestion control in VANET. Dr. Liu, you may please start your presentation.
Hello, can you hear me? Good morning, everyone. It's really early in Canada now. It's 4:30 a.m. Okay. My name is Xiaofeng Liu from University of Windsor, Canada. Today, I will be presenting our work on using deep reinforcement learning to solve congestion control issues in VANET. Here is the agenda for my talk. I will start by defining the problem of channel congestion in safety messaging and move on to our deep Q-learning solution. And finally, I will share our simulation results. A vehicular ad hoc network, we call it VANET, is a kind of a decentralized communication network that allows moving vehicles and roadside units to exchange real-time data to improve road safety and traffic efficiency. In VNet, the safety relies on the continuous exchange of we call basic safety messages, or BSMs. These messages broadcast periodically to all the other vehicles. The data includes like position, velocity, and so on. For example, how many messages per second the vehicle will send. However, in dense traffic, too many vehicles, this high frequency broadcasting will lead to severe channel congestion, which is the primary challenge. So that's why our paper tried to solve this problem. So in VNet, BSM plays a very important role, and we do use the sensor on the vehicle, the optical sensor, and the other sensors. We use wireless transmission, and so for BSM, the vehicles will send them periodically every second the vehicle will send 1, 2, up to 10 BSMs to all the other vehicles. And all the transmission will on the a single channel. The bandwidth is 10 megahertz, and the number is 172. It has been defined by FCC. So the problem is when we have very high vehicle density, then the channel congestion could happen. And we do have a lot of traditional approaches to solve this problem, but like we call it rule-based, means if the traffic is high, then the message is sent less and less. But this is a kind of there's a kind of problem. So we always have the dilemma, like if you send more messages into the channel, then it will cause channel congestion, right? Okay. So when we found channel congestion, we send less messages to the other vehicles. Another problem will be there. It's called awareness. When you send less messages to the other vehicles, then the other vehicles will be difficult to hear you. Then the safety can be also a problem. So this is a dilemma. So we try to find a smart way to solve this problem. The method we use is reinforcement learning. Why we select the reinforcement learning is it's a very useful tool to solve the problems with Markov property. So the so-called Markov property means the future is independent of the past given the present. Like a vehicle will send BSMs to the other vehicles. Okay, how the vehicle sends the messages to the other vehicles at the current moment has nothing to do with the past, how the vehicle sent to the vehicle. So we only focus on the next moment. So then we try to, reinforcement learning is a useful tool. That's why we can create the environment and all the other elements of for the approach. So in this approach, agent is our vehicle. The vehicle will send the messages to the wireless channel, including all the other vehicles. And the action can be what is the frequency the message will be sent, like how many BSMs per second, or what kind of transmission power the vehicle will use. The vehicle will select a kind of action and execute the action, then observe the environment to get, okay, how busy the channel will be and to calculate the reward. This is the basic principle. So why we use deep reinforcement learning and in this paper, the reason is we tried the standard Q-learning of reinforcement learning with limited state and action space. Like we defined only 10 beacon intervals from 1 BSM per second up to 10 BSM per second. This is not very ideal for very fine-grained control. And because the message rate is has only 10 message rates. So standard Q-learning is good for this kind of small state action space because we can use the tabular to calculate and record the Q values. However, if we want to have a better control, means we can let the vehicle have more selections to send the BSMs, then we need to define a large state and action space. In this case, the traditional Q-learning will not work because the size of the table will be very, very huge. That's why we select the deep Q-learning to solve this problem. Here is the architecture of our algorithm. You can see that In this architecture, we have a customized environment. This environment is very important for the whole simulation. And we use the two neural networks to finish the training. The reason why we use two neural network is with traditional deep learning, when we calculate a loss function, the target value is always stable. So when we calculate the gradient descent, it's easy that the neural network can converge. However, for deep reinforcement learning neural network, the target value, the Q value, changed drastically, which means if we only use one neural network, it's very hard to get converged. That's why we use two. The second one is called the target network, and the values in this target network will change slowly. For example, we change the value every 10 episodes in it. So it will get the make the training converged quickly. Let me introduce the how we create the elements of the reinforcement learning environment. The action space, we define the 150 discrete actions. So the actions here is we call beacon intervals, like every 0.1 seconds we send a BSM, or every 1.5 seconds we send BSM. The step size is 0.10 seconds. You might think why I define this from 0.1 up to 1.5 seconds. There's a reason, because we think for safety message, if the beacon interval is over 2 seconds, then this message is basically useless, right? So I define the maximum beacon interval is 1.5 seconds. For the state space, we define the tuple. It's called the channel load, channel busy ratio. How many times, how many percent the channel is busy. And the second element is called vehicle density, because it's a very important factor we have to consider when we calculate the channel congestion. We define the vehicle density, that how many vehicles around us in 100 meters. So that's our state and actions definition. Let's see the reward function, which is very, very critical as to how we train the agent. So the objective for the reward function is to maximize the message rate without exceeding congestion threshold. For example, we want the channel not very busy, not over 60%. Okay, we want to control the channel under 60%. It's a threshold. Okay, then we define the equation here. By defining this reward function, we can calculate the Q value and to see which is the best action for the vehicle next moment. The basic logic here for this equation is if the vehicle found select the action, like for example, a
Excuse
beacon
me, sir.
interval to.
I'm sorry to interrupt you. This is just a gentle reminder that 2 minutes of your presentation is
Okay. So this is the reward function definition, and we define the customized environment. Currently, we don't have any existing environment in OpenAI Gym environment. So I run almost 200 simulations to get a equation to calculate the channel load model. Then, based on the algorithm and the definition of the reinforcement learning, we set up a simulation. This is the environment, and this is the result. And we run two different kind of vehicle density. One is with 300 vehicles, another one is 500 vehicles, representing lower and higher vehicle density. We can see this, the channel busy ratio for our algorithm is the best one. We compare different approaches. So in my opinion, though, we propose this deep learning framework and we define the action states and we develop the environment. So it's a very interesting try. So thank you very much. If any questions, please let me know.
That was a very good presentation. I don't have any questions. Thank you so much. We can move forward with the second presentation for the day.
Thank you. I'm listening.
Thank you, Dr. Liu, for this presentation. And I'd like to take this moment to introduce our session chair.
Sanskriti, am I audible?
Yes, ma'am, you're audible. I'd like to welcome Dr. Vedima Dullo, who is our session chair for today. She's a professor at Lovely Professional University in Punjab, India. She specializes in marketing, consumer behavior, and the application of artificial intelligence without management. Her key research areas include AI in marketing, service marketing, consumer behavior, and information technology, with a particular focus on data-driven and technology-enabled marketing strategies. Welcome, ma'am. Would you please like to share a few words with us?
Thank you so much for giving me the opportunity to serve as a session chair for this prestigious conference. And I'm looking forward to listening to all the bright candidates who are here going to present their presentations. Thank you so much, Sanskriti. Wishing everybody all the very best.
Thank you, ma'am, for your encouraging words. Now we'll be moving on with our next presenter. We have Franz Obermeier presenting applications of virtual reality for the evaluation of manual assembly processes in industry, a Scopus AI-aided systematic review.
Yes, thank you. And welcome to our speech. Can you see my slides now?
Yes, sir, it's visible.
Perfect. So the topic today we will present is we will to show some applications of virtual reality for the evaluation of manual assembly processes, which is Scopus AI-aided systematic review. My name is Franz Obermeier. I am professor in the University of Applied Science Upper Austria. Since years, we deal with virtual reality and engineering topics. We created this paper with my colleagues, Professor Wolfertsberger, Feichtenschlager, Althaler, and Bronner. After a short introduction, we want to show our methodology used, then how virtual reality is in generally used in product development processes, and especially our topic today, how virtual reality is used in manual assembly processes. Yeah, virtual reality is currently used in industrial production for, of course, product development processes, especially to make some design reviews to optimize products. Our focus is process development, which means we optimize assembly processes, make assembly analysis to have optimized assembly processes out of virtual optimizations. And with this created virtual model, we can, of course, build and make some employee training. So the target in this article as shown is virtually used for assembly processes, to optimize assembly processes. And how can VR used in for assembly processes? At first, we can start with assemblability checks. Is it possible to place the part in the right sequence on the machine or on the truck? And after this, of course, we can optimize the workstation, virtual process planning on the workstation. Of course, out of this, we can optimize the whole factory, the whole assembly line. But it's not only important to assemble the part in the right way, it's also important that this machine or truck or car can also be repaired or maintained. So during this test, it's normally also possible to make some ergonomical innovations. Is it possible to optimize the workplace also for the people on the assembly station? Yeah, assembly process need also some tools and fixtures. Is the tool the right for the assembly processes? Can we easily assemble a screw with the right tool? This can also be optimized and will be optimized for assembly processes. And after that, of course, when the virtual assembly process is optimized, we can train people in this virtual area before we let the workers jump in the real assembly line. Yeah, the methodology used for this paper, we used a traditional way, which is, of course, with some searching, screening, manual extraction, and manual synthesis. With the traditional way, with papers from Google Scholar, IEEE, elsewhere, and so on. With the traditional way, we found 27 papers relevant for this article. Parallel, we used also Scopus AI, where, of course, we found out some helpful information, but we did not use this information. We just find and identified 14 more relevant papers, and we made the manual extraction and manual synthesis by our own. We also included some actual industrial applications where some companies like BMW or others present their results in virtual reality on their homepages. So we found out 6 sources and implemented them for virtual reality in manual assembly processes in this paper. Yeah, generally, virtual reality product development process could be divided in target definition, concept development, series development, and then the series startup following start of production. Within this product and processes, virtual reality is used to optimize design reviews with the benefit of a scale 1-to-1 in VR. Manufacturing optimization, we take the focus on assembly processes and their optimization. And of course, we can use this virtual model also for training and education. Main focus, virtual application in assembly. As we have said, we use VR for assembly ability checks. Can the parts be installed and also removed for maintenance? Is it easy to handle these parts and tools in the workstations, in the process planning, where to place the resources like tools and parts on the workstations and to optimize here the workflow. Also for the complete line, ergonomic elevation, at first injury prevention, comfort improvement for the workers, because the workers should be able to do the job for the next 20 years and not just for 1 month or 1 year. And of course, virtual training, safety training, skill enhancement is already done in the companies we work around. Some examples for this examplability check in virtual reality. Here, a real worker makes some tests and tests can the parts be installed without collisions? Is here accessibility ensured? Is it easy to handle the parts? Are they too heavy, too hot, or whatever? Can I see the things I should do? Is the assembly sequence correct? So this is what the industry around is doing at first in virtual reality for assembly processes. One point, for example, is the tool okay and the fixture for these parts correct? So in the left video, we see here on the assembly line, on the real assembly line, the worker uses here automatic torque wrenches, where with automatic torque wrenches, the screws are screwed in, and of course there should be place for this automatic tool. Parallel, we check also because if a truck or machine should be repaired on a station worldwide, for example, in South Africa, then the shop floor does not have this automatic tool. They have standard tools. And also with the standard tools available in the real workshops, they should be able to repair this machine or truck. And this is also, these things are tested virtually. Virtual process planning, here is a nice example from Bortolini et al., where, of course, we see here in the picture the virtual workstation. And on the virtual workstation, we can also check the ways the people have to go. Are the tools and the parts correct placed on the workstation? And therefore, we can reduce waste, and of course, we can reduce time to assembly these parts. Yeah, virtual training. On the right side, we see paper-based training. On the left side, we let the people train virtually, and the results by this virtual reality and paper-based check, we can see at the wiring time per unit, and we see that especially for beginners, for new people, that the virtual training is better, and we can reduce the training time and reduce the errors on the assembly line. For basic qualified or experts, we can see a difference if they use paper-based training or virtual training. So especially for beginners and new people, virtual training is also helpful for these people. Yeah, for a short summary, virtual is a new key technology to improve manual assembly processes. In the context of assembly, virtual is used to test the assembly, to test the maintainability, to improve fixtures and tools, to perform very good economic assessment, optimize workstations, line layouts, and support training programs. Future improvements in VR are expected in better user interaction, real-time collision detection, didactically structured training programs, and of course the use of AI. Overall, virtually will continue to enhance safety, economics, quality, cost effectiveness of manual assembly processes. Yeah, thanks for your attention. If there are questions, please feel free to ask. Thank you.
Yes, so thank you so much for your presentation. I would like to know, why did you choose virtual reality as the primary method to evaluate screw accessibility instead of physical prototyping?
Virtual reality instead of physical prototyping.
Yes, sir.
Physical prototyping is, of course, relevant, but the good thing of virtual reality is that we can do it in a very early development stage. So we can optimize manufacturing or assembly processes based on virtually ideas on the first CAD design. So the good thing in virtually is that we can do it earlier than with physical or with real parts. Yeah.
All right. Oh, thank you so much. Thanks a lot.
Yep.
Thank you, Mr. Obermeyer.
Thank you.
Dr. Tiller. Yes. Next, we have Yair Newman presenting Automated Detection of Acceptive and Dismissive Dialogue Acts, a synthetic LLM-based dataset.
So, thank you for joining my talk. I'm going to speak about the automatic detection of acceptive and dismissive dialogue acts. And I will first start by defining what I mean by dialogue acts. So the idea is very simple. When interacting, people use dialogue acts to convey their intentions. A simple example is an apology. And dialogue acts encapsulate an expectation for a response. Again, when I'm apologizing, I'm expecting forgiveness. But in practice, dialogue acts may be responded to positively by an acceptive response or negatively by a dismissive response. In the case of apologizing, apologizing may be met with forgiveness or conversely with resentment or anger. Now, the gap in the literature is that, to the best of our knowledge, there is no large data set of utterances expressing these two types of responses, and we are unaware of any machine learning model that can classify utterances or responses as either acceptive or dismissive. So the aim of the present paper was to create or generate an artificially generated data set of acceptive and dismissive dialogue acts along with a trained model for identifying them. So we built the data set through several phases. In the first phase, we generated a synthetic data set of utterances expressing 10 speech acts. And the speech acts were expressing empathy, greeting, taking a leave, criticizing, apologizing, complimenting, and so on. These are very typical speech acts people use in order to convey their intentions in dialogues or conversations. But to contextualize these speech acts in different scenarios, we identified 100 daily social interaction scenarios, such as classmate participating in debate and parent helping child with homework. And by using ChatGPT as the large language model, we generated a data set of approximately 1,600 utterances expressing these speech acts in different situational contexts. And this data set was used as an intermediate data set for developing the primary data set. Now, first we validated the data set using zero-shot classification. We hypothesized that if the large language model generated utterances that were validly corresponding to the speech acts, then a zero-shot classifier should classify the dialogue acts successfully. So we used the utterances, entered them into the zero-shot classifier with 10 labels, which are the labels of the speech acts. And what we actually measured is the performance of the classifier in classifying the speech acts. We use the chi-square to measure the statistical significance of the association between the original label, for instance, apology, and the classifier's decision, and the association was not only statistically significant, but extremely strong. So this result supports the validity of the first data set. Now we move to generating the main data set. We use the utterances generated in the previous phase in order to generate dataset 2, which includes the original utterances, and for each utterance we have two possible responses. One response is acceptive, while the other is dismissive. And the detailed prompt used for this task are presented fully in the paper we submitted. So we have the second data set with 3,140 utterances, and the data set consists of the original utterance, of course, the label of the dialogue act, whether it is empathy or apologizing, etc., the response to the utterance. For instance, a response to empathy is, oh, stop with the fake sympathy, you don't really care about how I feel, which is a dismissive response to the expression of empathy. And finally, we have the numerical label indicating whether the response is dismissive, one, or acceptive. Now, we have a data set with utterances and two possible responses for each utterance, and we move on to the validation of the data set. The first validation was a human validation. We gave a sample of the cases to undergraduate students and asked them to decide whether the response expresses an acceptive or dismissive response. The student judged a sample of 100 utterances, and the binary judgment, whether it is an acceptive or dismissive response, totally or perfectly agreed with the utterance's original labels. The second validation was zero-shot validation. We enter the utterance as an input to the zero-shot classifier and use two labels, acceptive response or dismissive response. And the output was the classifier's score, actually decision. And what we did is we actually used the two scores generated by the classifier as features or predictors in another machine learning classifier, which is boosting classification, because the zero-shot classifier is quite a weak classifier. Now, the hypothesis was that if the data set includes valid cases of dismissive and acceptive utterances or responses, then the boosting classification will successfully differentiate between the two responses based on the scores generated by the zero-shot classifier. And when we used five-fold boosting classification, we gained an average of 87% accuracy, precision, and recall, which is a result also supporting the validity of the dataset. Next, we trained and tested a very simple machine learning model, which is a model used to classify responses as dismissive or acceptive. The first test, we used the set-fit model and hypothesized that if the dataset contains utterances that validly expresses acceptive versus dismissive responses, then the set-fit trained on 20% of the dataset will successfully classify the responses on the rest of the dataset, and we gain a very high accuracy, precision, and recall, as you can see below, 98% accuracy, average accuracy, precision, and recall. Now, the second test suggested that if the set-fit model identifies patterns of acceptive and dismissive communication, then it can be used for other tasks as well. And to test the validity of the model, we used cross-domain validation and evaluated the performance of the model on identifying polite versus impolite utterances. And we hypothesized that if the model is successful, then it can identify polite utterances that are actually acceptive and impolite utterances that are quite dismissive. Now, we used the daily dialogue dataset with politeness scores produced for each utterance and measured the performance of our model. For the analysis, we use utterances ranked in the top 25% of the daily dialogue dataset, meaning polite utterances, and the lowest or the bottom 25% of the utterances, which is defined in the dataset as a group 3, impolite utterances. And the results were that the classifier gained 82% accuracy, around 80% accuracy, recall, and precision, which is quite good because it is a significant improvement over the baseline for prediction, which is 50%. Half of the cases are impolite, the rest are polite. So it's an average improvement of around 30%. So what we can see is that the model trained on identifying acceptive versus dismissive utterances or responses can also identify politeness. The third test was the mental health support dataset, in which we used our model to identify utterances classified or labeled as empathic on a binary scale 0 to those expressing full empathy. We analyzed only empathic responses and responses in which empathy is not expressed. It doesn't mean that it is not empathic, but it means that empathy is not expressed. The majority of the cases in the data set included, 93% included non-empathic responses. And the results was that the model, in the case of responses with no empathy, it recorded around 78% of the cases. And in the case of the minority class of empathic responses, it identified 70% of the cases. Given the small proportion of empathic responses in the dataset, around 7%, we can see that the performance are quite good. The last dataset we used was a dataset of couples in conflict. Drawing on my expertise and the GPT model, we identified daily situations that cause conflict for a couple and dialogue acts that can escalate or de-escalate the conflict. So we created quite, I'm running over the details, but we generated a data set that expressed these conflicting situations in across different classes of English speakers. And we had 1,200 unique dialogues in which one of the couples is saying something and the other responds, whether empathically or non-empathically, in an escalating or de-escalating way. And the results was that the set fit prediction, prediction.
Sir.
Yes.
Sorry to interrupt you. This is just a gentle reminder that 2 minutes are left for your presentation.
I'm with the timer near my table, so I'm fine with time. Okay, thank you. So what we can see is that we had a very good performance with approximately 86% accuracy. So in sum, we provide a novel synthetic data set. We have a machine learning model, but an important qualification, the rapid advancement of large language modules overshadows the set-fit model. So we can use now large language models. However, fine-tuning a large language model and correctly prompting it may benefit significantly from the resources that we developed and the specific prompts that we use and introduce in the paper. Thank you.
Thank you so much for that insightful presentation. It was a very good work. I just have one question for you. Why did you choose zero-shot classification specifically for validation?
So the first idea was to use a very, very simple and primitive device in order to have a general view. Next, we use the scores of the zero-shot classifier as predictors for boosting classification. So it was a very easy and primitive way to validate our model without too much sophistication. That's all.
Okay, thank you so much. Thanks a lot.
Thank you, Mr. Neiman. Dr. Lillo, for this discussion. Next, we have Michelle Gordon presenting Digital Literacy Indicator Map, a multidimensional measurement application.
Good morning. Thank you for being here. I'm Michal Koren from Shenkar. Today, I would like to talk about something that sounds simple, digital literacy measurement. But the real question behind it is actually much bigger. If governments are digitizing everything, how do we really know who is able to participate? And more importantly, where exactly the gaps are? That's what the Digital Literacy Indicator Map tries to answer. This research was conducted in collaboration with Professor Shazaf Rafaeli and Or Peretz from Shenkar. Today, digital participation today is not optional. If you want access to work, to healthcare, to financial services, to rights, you need digital capability. And yet, we often treat digital literacy as if it is only technical skill. It is not. It also confidence, trust, risk perception, and ultimately whether someone actually chooses to engage. Over the past decade, multiple international surveys have attempted to measure digital literacy at scale. These efforts are extremely valuable. Most of them rely on composite indices, which are very useful for marketing and comparison, but they are less effective for diagnosis. Policy makers need to know not only who is behind, but where the gap lies and what drives it. So this is most current approaches rely on composite indices. We aggregate everything into one number. That's convenience, it's clean, it's easy to compare. But it hides important differences. For example, two people can have the same digital literacy score, but for completely different reasons. One may lack knowledge, another may know perfectly well what to do, but does not trust the system. From a policy perspective, those are entirely different problems. If we don't separate them, we design generic interventions, and generic interventions are usually inefficient. So the problem is not that we measure digital literacy, it's how we measure it. This is where the ABK framework comes in. We distinguish three strands: knowledge, attitude, and behavior. Knowledge is the cognitive layer, understanding how tools work. Attitudes are about confidence and trust. Do I feel safe? Do I believe this system is fair? And behavior is actual engagement. And here is the important part. These three don't always move together. Someone may have knowledge but no trust, or positive attitudes but low skills. Separating them gives policymakers something actionable. It tells them what kinds of intervention is needed. Building on ABK, we structured digital literacy as metrics. On one side, skill families, information management, communication, transactions, problem solving, and AI literacy. On the other side, life domains, employment, health, finance, learning, consumer life, rights, and safety. Because digital skills don't exist in collaboration, in abstraction, they exist in context. Doing a financial transaction is not the same as accessing a health portal. By preserving both dimension, skill, and context, we avoid flattening the problem. Each cell contains separate knowledge, attitude, and behavior indicators. So instead of one number, we see patterns. A key addition here is AI literacy. AI systems increasingly mediate access to information and services, search engines, recommendation systems, decision support tools, public service algorithms. Engaging with AI requires more than knowing how to click. We define AI literacy through 4 components: awareness, knowing where AI operates; usage, the practical interaction; evaluation, critical thinking about outputs; ethics, understanding bias and fairness. Without these competencies, people rely on systems they don't fully understand, and that has governance implications. All of this operationalized through interactive ICICT dashboard. The system integrates 184 validated indicators drawn from established national and international survey instruments. So rather than reinventing measurement, we reorganize and harmonize existing validate metrics within diagnostic structure. All indicators are aligned to 0 to 100 scale, which enables comparability across domains and populations. We combine self-reports and performance-based items to capture both perceived and demonstrate capability. Let me briefly show you how the platform works. As you can see in video, rows represent the skill families. Okay, column represent the life domains. Each cell contains indicator separated into knowledge, attitude, and behavior. The colors follow traffic light logic, highlighting of relative strength and potential bottlenecks. Through drill down, you can click on any cell like this and immediately view the underlying indicators. So instead of asking, is population digital literature, we ask in which domain, in which skill, in which dimension. And that shifts the conversation from description to diagnosis. Methodologically, we made one deliberate choice. We do not automatically collapse everything into one score. ABK dimension are reported separately. Aggregation is possible, but it's optional and transparent. We also preserved distributional views because average can hide a severe subgroup disappears. The goal is not elegance, the goal is clarity for policy action. So what does this enable? First, bottleneck detection. We can identify identifying very specific gap. Second, targeted program. If the issue is knowledge, we train. If it's trust, we redesign communication. If it's behavior or friction, we improve usability. And third, progress monitoring. It's monitoring over time. We can track shifts in specific domain. And fourth, international comparability. It turns measures into policy instruments. So to conclude, this framework moves digital literacy measurement from aggregated indices to structured diagnosis. It preserves life context, it separated knowledge, attitude, and behavior, and it integrates AI literacy into broader digital inclusion agenda. But more than that, it shifts a role of measurement itself from something we use to rank populations to something we use to guide intervention. Because digital inclusion is not only about access, it's about real capability. And capability must be measured in a way that reflects how people actually live and engage. Thank you.
Thank you so much. So I really appreciate the framework that you have incorporated in the study. What I would like to know from you is how did you handle conflicts or the inconsistencies when harmonizing data from national versus international sources onto your 0 to 100 scale?
Okay, that's exactly why the structure. Okay, at this stage, the contribution is primarily diagnosis. Implementation can be modular, so governments do not need to deploy the full metrics at once. The framework allows a selective focus by domain population or skill family. And we, based on international survey, to validate the indicators. At this stage, the framework integrates indicator drawn from previously validated national and international instruments. The harmonized process focused on scale alignment and conceptual consistency within the ABK structure. Large-scale empirical validation is part of the next phase, including reliability testing and outcome linkage.
Right, okay, fine. Thank you so much. Thanks a lot. We can move ahead with the next presentation, please.
Yes, ma'am. Thank you for the presentation. Now we have Sneha Krizanik presenting exploring the use of artificial intelligence tools by computer science students in Solidity smart contract development.
Hello, everyone. I hope you can hear me. Do you hear me?
Yes.
Yes, you're audible.
Okay, thank you very much. Thank you for your very interesting presentations. Today, I'm going to present you our work under name Exploring the Use of Artificial Intelligence Tools by Computer Science Students in Solidity Smart Contract Development. So we already know that artificial intelligence is influencing our lives, our ways we work, but artificial intelligence tools are increasingly transforming the way we program, the way programming is taught and practiced, influencing not only traditional software developments, but also fields like blockchain and Solidity smart contracts development. Solidity is a primary language for programming on Ethereum. Ethereum is an online virtual machine for blockchain, and Solidity is gaining prominence in university curricula. Understanding how students use AI tools while learning to program smart contracts is very important for aligning education with technological advancements and the needs of modern software development. So, what were our aims? The first aim was to determine the extent to which students utilize AI tools while programming smart contracts in Solidity. The second aim was to identify the types of problem-solving tasks for which these tools are perceived as most beneficial, to evaluate whether the current curriculum and teaching practices sufficiently address the evolving needs of students, and to provide recommendation for updating course content and instructional strategies in line with student experiences and technological advancements. So, something about methodology. This study was conducted at the end of the second semester in 2025, which lasted from early March to mid-June in Croatia. This research focused on students on their final years of study enrolled in a course related to electronic business. Through the semester, students participated in weekly laboratory exercises in which they programmed smart contracts in Solidity. They were receiving smaller assignments each week based on specific real-world use case, as well as they had project assignment that required them to design, to implement, and to test a complete real-world smart contract solution. Following the completion of course assignments and the test project, there was an anonymous and voluntary online survey using Google Forms. The purpose of the survey was to gather students' perception and experiences regarding the use of AI tools during the process of programming. Students were asked whether they used AI tools, which specific AI tools they used, how frequently they used them, for which types of programming tasks. They were also asked whether AI tools were helpful for them, whether students believe they could have completed their assignments equally well without using AI, and whether these AI tools contributed to new learning, and to what extent students relied on their own knowledge. And this question was very important to us. Of the 94 completed surveys, over 96% of students indicated that they had used at least one artificial intelligence tool while working on Solidity smart contracts on course. According to this figure 1, we can see that students most commonly used ChatGPT. So ChatGPT is by far the most dominant tool among students. But this second question, allowed multiple responses. So after ChatGPT, the next most frequently used tools were DeepSeek and Remix Copilot. Remix Copilot is integrated within Remix Ethereum online virtual machine. The next question was how frequently students used AI tools like ChatGPT while they were working on their project assignments. So the majority of students, over 44% of them, selected the midpoint value, 3 on a scale from 1 to 5, indicating a moderate frequency of AI tool usage. The next most common response was 2, over 93%, while 16% of students reported frequent use, rating 4, and over 9% reported very frequent use, rating 5. Students were also asked how frequently they used AI tools when solving individual assignments, such as those given during laboratory exercises. The largest group of students, 33%, selected a rating of 2, suggesting relatively infrequent use of AI tools for these tasks. Only 4%, over 4% of students indicated very frequent use, rating 5, while 16% of students reported that they rarely used AI tools. Students were asked to provide open-ended responses about which specific tasks within the project assignment or laboratory exercises they most frequently used AI tools for. So they said that they most used AI tools for code debugging, for writing functions, for generating ideas. They used AI tools to explain existing code sections, check code syntax, and assist with smart contract testing. They said that AI tools were helpful for clarifying unfamiliar terms, improving understanding of Solidity programming concepts, and suggesting ways to optimize code. Some of them told that using AI tools was easier for them than Googling the problem. The results showed how useful students found AI assistance while working on their project assignments. So according to this figure 2, we can see that the vast majority of respondents rated the usefulness of AI tools highly. So over 40% of students selected the highest rating, 5, and over 36% choose 4 on a scale from 1 to 5. The results show student perceptions on whether they could have completed the project with the same quality without using AI tools. So the largest group of students, as we can see, over 42% answered no, indicated that they believe AI tools were essential for achieving the quality of their project. So this does not mean that they would not complete their projects, but they believe that their projects would not be of the same quality without using AI. In the survey, respondents were asked whether they had learned something new about Solidity or programming in general. So the vast majority of students, over 93% of students, answered yes, indicated that AI tools contributed to their learning. The very important result for us as teachers was the information on how much students relied on their own knowledge compared to what was generated by the AI tool. The majority of students reported a high level of reliance on their own knowledge. So over 44% select a rating of 4, and over 36% choose 3 on a scale from 1 to 5. Additionally, over 7% of students gave the highest rating, 5, indicated that they relied almost entirely on their own knowledge. Only a small number of students reported low reliance on their own knowledge. 1% selected 1 and over 10% selected 2, meaning that these students mostly depended on AI-generated content. So what would be recommendations for teaching strategies and curriculum development? Recommendations are explicitly integrate discussions and demonstrations of AI-assisted coding into the curriculum. Practical sessions could include guided examples of how to critically assess and verify AI-generated code, fostering the development of both and technological skills and critical thinking. Assignments and exercises should be designed to encourage responsible and reflective use of AI, creating learning environments that promote a balanced approach, emphasizing the strengths and limitations of AI in programming, and opportunities for peer discussions, collaborative projects, and industry engagement. So industry engagement can further support student learning and readiness for real-world challenges. Given all this rapidly evolving landscape of AI technologies, we can say that regular curriculum updates are already necessary to keep pace with new developments, tools, and industry expectations. So, what to say in conclusion? All this widespread adoption of AI tools for problem solving, debugging, and understanding complex programming concepts demonstrate that students are developing not only technological proficiency in programming, but also digital literacy and the ability to critically evaluate AI-generated content. Integrating ethical and responsible AI use into the curriculum further supports the development of adaptable and employable professionals capable of meeting the demands of an evolving labor market. Thank you for your attention.
Thank you so much for that presentation. It was very well presented. Your entire paper was basically on descriptive analysis. What I would suggest is that in future presentations, you can also incorporate inferential analysis. So that's all from my side. Thank you so much.
Thank you for your comment. I appreciate it.
Thank you.
Thank you, Ms. Prasanth. Now we have Ms. Anya Cotton Clarkson presenting success factors and challenges in the organizational implementation of chatbots, a comparison of Germany and China. Do we have Ms. Clarkson with us here? Okay, so we are done with the presentations for today. I sincerely thank all our authors for the excellent presentations and valuable contributions to the session. I also extend my gratitude to all participants for being a part of this international conference. I hope this session was informative as well as insightful. On behalf of the ICICT team, thank you for your continued support during the 11th edition of ICICT, as well as all the previous editions. We look forward to welcoming you again for the 12th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The publication is expected to be available within 7 to 8 months. We kindly request your cooperation with the ICICT 2026 during this process. I would also like to thank our session chair, Dr. Ridhima Dullo, for joining us today. As a token of our appreciation, we present this to you.
Thank you so much. I really appreciate that.
May I please request everyone to turn on their cameras so that we can have a snapshot of this session. Thank you everyone for joining us.